Good day. We are the Group 1, composed of Lawrence Ares, Mark Hekilan, and Derlene Sanchez. We will be discussing about the basics of fluidization. Before digging deeper on the mechanisms and definition of fluidization, let us first recall some important terms that are used in our lesson. So the first term is a fluid. So a fluid is a substance that does not resist distortion and hence will change its shape. So in other words, it is a flowing substance. A fluid can either be a gas or a liquid, as these two follow the definition of a fluid. The next one is the superficial velocity. So, when a fluid is passing through a porous media in a pipe, the superficial velocity is the velocity of a fluid when passing through the same pipe without any hindrances to its flow. So, it is just the velocity without any obstacles to its fluid path. Now, what is fluidization? Fluidization is the phenomena where solid particles exhibit fluid-like behaviors, such as the ability to flow or to be pumped using equipment for fluids by setting the required conditions. Then, what are these fluid-like behaviors? These are the ability to flow, ability to be pumped using equipment for fluids, and to take shape of its container. The required conditions for this to happen will be discussed in further slides. So basically, it just means that this process enables particulate matter to flow through pipes, which is widely used in some industrial processes. How does it work? Let us take a closer look. So first, the particles are initially at rest in a pipe. At this moment, the particles do not move nor exhibit any kind of movement. Next, a fluid, which can either be a gas or a liquid depending on the use, is injected at the bottom of the pipe. So, when a fluid is passed through these particulate matters at rest, the fluid flow agitates these particles at rest, creating spaces between particles. And as the fluid velocity is increased, it reaches a point where the upward drag forces brought by the fluid is equal to the force exerted by the particulate matter. And as the drag force equilibrates with the gravitational force, the separation of particles become more and more apparent. Moreover, this is also the point where the solid particles exhibit fluid-like properties as the solid particles flow freely along with the fluid. This velocity is called as the minimum fluidization velocity. In addition, it is also the superficial velocity that a fluid exhibits at this particular moment. Minimum fluidization velocity is the minimum velocity needed to fluidize a set of particles. This flow is caused by the pressure gradient in the pipe. However, as the fluid rises through a bed of particles, pressure drop is observed to increase caused by frictional resistance due to the contact of the fluid and particles and pipe walls. And upon closer look, it can be observed that the particles are colliding and bouncing off each other. To highlight some important terms from the preceding slides, the minimum fluidization velocity is the superficial velocity exhibited by a fluid at the start of the fluidization, where solid particles start to gain fluid-like properties, or it is simply the initial velocity needed to fluidize the system. It is the baseline data needed to fluidize the system. However, this data may sometimes not be accurate, hence the term baseline. And another thing is the pressure drop. So, as the fluid rises, pressure drop also rises due to increased contact of the particles and the pipe walls. It is described by the formula, which will be derived on the next slide. So now, we have here particles in a pipe with a fluid passing through its bottom. So now, consider one particle and do force balance. The forces that are acting on a particle is the fluid pressure force and the fluid drag force, while the forces or the force acted by a particle is only gravitational force or simply the weight of the particles. Writing this into equation gives us this. Remember, the 1 minus epsilon should always be remembered since this term pertains to a fraction occupied by the particles in a pipe. Isolating pressure drop yields us this equation. Simplifying this by dividing area on both terms and by getting the gravity and the height and the 1 minus epsilon, which is common to both terms, would give us this simplified pressure drop equation. So now, how does the velocity of a fluid relates to the pressure drop? Their relation is shown by this graph. So at this part, the pressure drop linearly increases with increasing velocity. This is due to the increased contact of the fluid and the particles. So this is the point where the separation of particles remain constant. At point A, this is the peak of pressure drop. The increase in pressure drop is associated with extra force needed to separate compact particles. Since the particles may be attracted to each other in one way or another, it requires extra force to separate this. So, in addition to this, the extra force or extra pressure drop is associated to overcome wall friction and adhesive forces. Moreover, it is also at this point where the system starts to exhibit fluid-like behavior. Hence, this point at point A also marks the minimum fluidization velocity. After the separation of compact particles, the pressure drop lessens and remains constant as the fluid velocity becomes faster. This may be due to the fact that the system becomes a fluidized bed. Hence, the pressure drop remains constant as velocity is increased. The application of fluidization is in fluidized bed reactors, ion exchange particles, food and beverage, hydrometallurgy, water softening, and catalysis. Its common application in the industry is to mix all components in a fixed ratio. However, the type of fluid to be used depends on the application. In common cases, the usage of a gas as a fluid is observed in combustion mechanism or for mixing process, as gases do not react with particles or particles are not soluble in gases. So, mixing particles with another particles can easily be done by fluidizing it with a gas. On the other hand, the use of a liquid as a fluid is usually used in mixing process. So, one concrete example of this in the food and beverage industry is in a 3-in-1 instant coffee where particles of different properties are fluidized in order to be mixed completely. So now, how to determine the minimum fluidization velocity? So this can be described by the Cosen-Kármán relation with a formula presented on the screen, where the delta P is the pressure drop, H is the height of the fluid, U as the viscosity, epsilon as the porosity or the volume fraction, the UO as the minimum fluidizing velocity, and SV is equal to 6 divided by particle size. However, the SV values may depend on the shape of the system in question. However, for particulate matters such as this, it is equal to 6 divided by the particle size. So the Cosen-Kármán relation was given by this. However, from the preceding slides, we derive an equation for the pressure drop specifically for this type of fluid, as shown by this equation. So substituting the delta P here to the Cosen-Kármán relation gives us this equation. So canceling the common variables h on the left side would give us this. Isolating the UO or the minimum fluidizing velocity on the other side will give us this relation. So the minimum fluidization velocity can be described or can be obtained by this equation. Now, let us apply all those concepts and try answering a sample problem. So, a packed bed consisting of 1.96 kg of solids of density 2.8 grams per cubic centimeter with a particle size of 500 micrometer is contained in a cylindrical vessel of 10 centimeter internal diameter and the bed height is 20 centimeter. The fluid used has a density of 1000 kg per cubic meter and a viscosity of 0.001 Pascal second. Find the volume of the vessel occupied by the bed, the volume of solids in the vessel, porosity of the bed, and the minimum fluidizing velocity. So here, we are given the particle properties with a mass of 1.96 kilograms, a density of 2.8 gram per cubic meters, the particle size of 500 micrometer, and the bed properties with a diameter of 10 centimeter and a height of 20 centimeter, and the fluid properties with a density of 1000 kilogram per cubic meter and the viscosity of 0.001 pascal second. So, what is our approach in solving this problem? So first is to determine the volume of the vessel, which is described by the equation pi times r squared h. The second is to determine the volume of solids in the bed by dividing the mass of the solids divided by the density. The third one is to calculate for the bed porosity, where the volume of the container, which was obtained from the first method, subtracted by the volume of solids, which was solved from the second method, divided by the total volume of the container. And lastly, by those values, we can now obtain the minimum fluidizing velocity as shown by this equation. Now, let us calculate the volume of the vessel. So, where the properties are given or summarized by these values. So, the formula is equal to pi r squared h. And recalling that the radius is simply diameter over 2, and by substituting these values to this formula, it will give us this equation. Simplifying, therefore, the volume of the bed is equal to 500 pi cubic centimeter. Now, let us calculate the volume of solids in the bed, where its properties are summarized by these values. So the formula for this is simply dividing the mass of the solids by its density. So substituting these properties to the formula will give us the volume of solids, which is equal to 700 cubic centimeter, which is presented here. Now, let us calculate for the bed porosity, where the values obtained from preceding numbers were summarized here. So the bed porosity, or the porosity, has the formula volume of container subtracted to the volume of solids divided by the volume of the container. So substituting these properties, we will have a porosity value of 0.554, 0.5544. So this value tells us the fraction of the container that is unoccupied with solid particles. Since the necessary values were already taken or were already solved, we can now calculate for the minimum fluidizing velocities, where the properties are summarized on this side of the screen. So the formula for this is given by our derived equation from before. So by direct substitution of the known values to this formula, we will arrive on this very lengthy equation. And simplifying this would result into a minimum fluidizing velocity of 0.0094 meter per second. So the minimum fluidizing velocity of the problem is equal to this value. It means after reaching this velocity, the particles will start to exhibit fluid-like properties.
In packed bed of small particles, when a fluid enters at sufficient velocity from the bottom and passes up through the particles pushed upward and the bed expands and becomes fluidized. Types of fluidization. There are two types of fluidization, and the behavior varies depending on the fluidizing medium used. If liquid enters at high velocities, the particles expand in such a way that the interparticle distance is uniform. As seen in the figure, the bed is homogeneous and the average bed density is the same in all regions. This is called particulate fluidization. This mainly occurs with liquid-solid fluidized system. An example would be a hot air popcorn popper. The popcorn kernels, all being fairly uniform in size and shape, are suspended in the hot air rising from the bottom chamber. Because of this intense mixing of the particles, akin to that of a boiling liquid, this allows for a uniform temperature of the kernels throughout the chamber, minimizing the amount of burnt popcorn. After popping, The now larger popcorn particles encounter increased aerodynamic drag, which pushes them out of the chamber and into the bowl. Another type of fluidization is when a gas is used as the fluidizing medium. As noticed in the figures presented, as gas velocity increases, a fraction of the gas will pass through the bed in the form of bubbles. As a result, the distribution of particles inside the bed is no longer homogeneous. The bed then appears to be divided into two phases, the bubble phase and the emulsion phase. At low gas velocities, the rising bubbles contain very few solid particles. The remainder of the bed has a much higher concentration of solids and is known as the emulsion phase. This type is called bubbling fluidization, and it occurs mainly with gas-solid fluidized system. Fluidized bed design. A typical fluidized bed reactor contains a plenum, a gas distributor such as a grid plate or sparger, particle bed region, a freeboard region above the particle bed, heating and cooling coils if needed, and cyclones as shown in Figure 5. Fluidized beds can be used as dryers and heat treaters. Their design is somewhat different from that typical reactor. For fluidized bed dryers and heat treaters, the bed heights tend to range from 0.3 meter to 0.5 meter, whereas fluidized bed reactors usually have bed heights on order of 1 to 2 meters. There are many constraints that need to be considered in the design of the fluidized bed to ensure reliable operation. We have grid plate and sparger which are subject to pressure drop and spacing limits. Entrainment rates also need to be measured, and cyclones must be designed for high collection efficiency and low pressure drop. First, we have distributors, which comprise the grid plate and gas sparger to provide good gas distribution, pressure drop, and spacing considerations. In order to have a good gas distribution and pressure drop, the number of orifices and its diameter need to be balanced. Otherwise, if the pressure drop is too low, the gas will be poorly distributed. Then we have particle attrition and erosion. Particle attrition occurs when the high-velocity gas jets from the distributor cause particles to collide with each other and with the walls of the vessel. It also occurs when particles carried by swirling gas flow collide at the cyclone inlet and throughout the cyclone region. Attrition is simply breaking down of particles, but it's not always necessary. Thus, the distributor needs to be designed in such a way that the gas jet's penetration length is less than the distance between the orifice and the vessel wall, for this will reduce erosion of the vessel walls and the internals as well. As the gas containing entrained particles flows upward, the larger particles may fall back into the bed. At some distance above the bed, the smaller particles remain entrained. This point is referred to as TDH or transport disengagement height. The TDH, entrainment rate, and the size of the particles are important design parameters for a fluidized bed. The TDH is required because the cyclone or vessel exits are commonly installed at or above the TDH to reduce the solid loading to the cyclones and minimize exit losses. The entrained particle size distribution is needed to size the cyclones and determine the collection efficiency. And lastly, the entrainment rate is needed to estimate the solid loss rate.
When the flow of a gas passed through a bed of particles is increased continually, the following can be observed. At a very low gas velocity, the bed remains fixed. Particles remain in contact with one another, and the structure of the bed remains stable. This type of bed is similar to packed beds. With increasing gas velocity, a point is reached where the drag force imparted by the upward moving gas equals the weight of the particles, and the voidage of the bed increases slightly. This is the start of fluidization and is called minimum fluidization. Increasing the gas flow further, the formation of fluidization bubbles sets in. At this point, a bubbling fluidized bed occurs. As the velocity is increased further still, the bubbles in a bubbling fluidized bed will coalesce, and grow as they rise. If the ratio of the to the diameter of the bed is high enough, the size of the bubbles may become almost the same as the diameter of the bed. This is called sludging. If the particles are fluidized at a high enough gas flow rate, the velocity exceeds the terminal velocity of the particles. The upper surface of the bed disappears, and instead of bubbles, one observes a turbulent motion of solid clusters and voids of gas of various sizes and shapes. Beds under these conditions are called turbulent beds. With further increase of gas velocity, eventually the fluidized bed becomes an entrained bed, in which we have a dilute fluidized bed, which amounts to pneumatic transport of solids. Under this dilute flow condition, the solid particles behave as individuals, fully suspended in the gas, and erotic dynamic forces dominate. When talking about a fluidized bed, one mostly refers to a bubbling fluidized bed as shown in Figure C. Gas fluidized beds are characterized by the bubbles, which form at superficial gas velocities that is slightly higher than that required to just fluidize the particles. How does these bubbles behave inside the bed? Gas is distributed from the bottom using a distributor. Near the distributor, the size of the bubbles are smaller compared to the bubbles formed above. This is due to the coalescence of the bubbles, where smaller bubbles tend to merge with other bubbles as they rise through the bed and form a larger bubble. The movement of particles in fluidized beds is known to depend largely on bubbles rising through the bed. The bubbles exert a very strong influence on the flow pattern in the bed and provide the mechanism for the high degree of mixing of solids. Therefore, special attention is paid to bubbles and their properties, like bubble size, bubble wake, and bubble rise velocity. When a bubble rises, it carries some amount of solids inside. This is called wake. The formation of a wake follows directly when the bubble forms. Hence, the bubble picks up most of its solids at the bottom of the bed as it leaves the distributor plate. Smaller bubbles merge to form larger bubbles as they rise through the bed. This larger volume of bubble has higher bubble velocity. Notice in this clip that the bubbles at the top moves faster as indicated by the red color. The behavior of bubbles inside the bed can be described using the Davidson and Harrison model. From experiments with single bubbles, Davidson and Harrison found that the velocity of rise of a single bubble could be related to the bubble size by this equation, where U sub br is the rise velocity of a single bubble and d sub b is the diameter of the bubble. However, when many bubbles are present, this velocity would be affected by other factors. The greater number of bubbles result from a higher superficial velocity. Hence, the larger the value of superficial velocity, the faster the velocity of a gas bubble as it rises through the bed. Other factors like viscosity of the gas and the size and density of the solid particles that make up the bed also affects the bubble rise velocity. Both terms also affect the minimum fluidization velocity. So instead of using viscosity and density, the minimum fluidization velocity will be used for the relationship. That is, the higher the minimum fluidization velocity, the lower the velocity of the rising bubble. Davidson and Harrison proposed that the rate of bubble rise in a fluidized bed could be represented by this equation, where U sub s is the superficial velocity and U sub o is the minimum fluidization velocity.